recorded. So I said take a picture of it, a photo with my SLR camera, and defocus on purpose to show the colors. And typically this would be a lot brighter than Bellatrix. So already in December, you were seeing that was fading beyond what we're used to seeing with Betelgeuse. So then I went back into that AVSO database of recent variable star estimates, and these are visual estimates. And what I noticed is it's just very noisy and not a very satisfactory brightness measurements. And so the data points are all over the place. And here it is fading, but who knows what its real magnitude is. So the next thing I did was went in and just looked at where people with the ability to measure it, not naked eye brightness estimates, where they measured, and even that is too noisy for my tastes. So I found out that a person who has a photoelectric photometer and runs that section in the AVSO organization, Tom Calderwood in Oregon, has real clean data, and he's able to measure these very bright stars as they vary. And so here it is starting to go through this kind of unprecedented fading, and we didn't know how faint it was going to be. So this is toward the end of December right here. And so then what I did after that was said, well, I want to see if I can measure this, because I do photometry every night with asteroids and then sometimes with variable stars and that kind of thing. So the typical way you do photometry is you have a target and then you have comparison stars in the field of view at the target. And that's the way it works, and you kind of calibrate off of them, and you can figure out what the actual brightness of Betelgeuse of your target is as it's varying there. The first problem you get into is I have a 12.5-inch telescope with a CCD camera, and the targets that I measure are 14th magnitude, 13th magnitude, sometimes even 15 or so. And so you take a really, really short exposure, a 1 second exposure, a 1/10 of a second exposure, and it's like asking how much water did I pour into a cup, but the cup has been running over for the last 10 seconds as I out of the faucet. And so you're saturating all these pixels, and what do you do about that? So the first thing you do is you make an aperture stop. And here's this high-tech thing that my wife Jennifer and I made. And we put 2 3-inch holes in it, and I said maybe that'll help, and I'll defocus the telescope on purpose to kind of diffuse that light and spread it out a little bit. So you don't have to read any of this, but what you end up with is when you defocus it, you get something that looks like a double star. But as long as that fits in that aperture, that middle aperture right there, you can do valid photometry. But the problem was, in order to not overfill the cup with water, in order to not saturate, I had to do exposures that were only 3/10 of a second. And that's kind of problem number one here. That's a big problem. You can't really do photometry with exposures that are that short. And the reason, and I hope everybody sees this thing animating okay, is just a simulation. This is a scintillation, which is different from seeing. That's the more large scale stuff that you see naked eye when you see stars twinkling. And so on the kind of time scale of a 1/2 a second or even 1 second, it can be varying by several tenths of a magnitude from 1/2 second to the next. So you take a single image and you're not going to get a good representation of its brightness because it's jumping all over the place. So you want to make that exposure longer if you can. And what that meant is I got to make smaller aperture stops. And so here's allowing for 10,000 models. Here's model 0002. And it has 4 1¼ inch holes. And so we did that to it, and everybody will recognize 1¼ inch is the size of an eyepiece barrel, so that's not a coincidence either. So we put these 4 smaller holes in there, and that's kind of the brightness profile that you get. And this is looking a lot better because nothing is clipped, nothing is saturated. So now you can measure the brightness of a 1st magnitude star. Unfortunately, you still have to do a real short exposure. I don't want to make those apertures any smaller, so I'm only able to get away with a 1.5 second exposure. So that actually worked, and I'm not saturating, and I can get measurements off of that. So at that point, I was ready, after a few days of these iterations and messing with it, to get going on it. So the next problem that you encounter, I showed that star with 4 other comparison stars that you calibrate off of in the same field of view, well, now your exposure is so short for Betelgeuse that you're not going to get any other stars in the field of view. You know, anything, even a 6th or 7th magnitude star that's in the field of view is going to be too faint, and you won't be able to compare it. So what that means is, to get your comparison star, you've got to slew the telescope. So you have to set up a script that goes over and slews to a different star. So here's Betelgeuse and Orion. And what I'm going to try to find, and this is with the help of Brian Skiff, we found stars that have similar color. That's important for some reasons involving our atmosphere, and they're stable. They're not stars that are variable themselves, because that would kind of kill the readings also. So you have the target, and then you go over to the comparison star, and the check star is a star of known magnitude that you're going to see how stable it is and how well it matches the catalog value. And if it matches real well, that means that your photometry of your target, Betelgeuse, is going pretty well. So there's a whole script that's set up to point at this, take 6 images, point at that, take 6 images, go back to that, take 6. So I would take, it actually was 24 images per set, and I would do 3 sets of them. And that way you can average out that scintillation, the twinkling of the star, and get a good statistical representation of the brightness with the errors. We're not going to look at that slide at all. We're barely going to look at this. Here's my spreadsheet that does all this stuff. What I would have to hand enter are these numbers in blue. There's 72 of them. That's a problem I created because I didn't know how to script that in any way or how to automate that. But that's going to give us what Aldebaran's brightness is, which is the comparison star. I hit that twice. There's the target, and this is the check star, which is a 4th magnitude star. And so what I was then able to do is do statistically just average what these are and get the error, get the scatter on that, and I'd make this chart. At the very end of it, I would have a chart that looks like this that gives me the magnitude of Betelgeuse and the error in all these 18 measurements I made of it. And then this is our check star, which should have a magnitude of 4.08. And that's kind of a key to this thing, to see how well the photometry is working. How well do I match that cataloged magnitude? So we're coming up on results now. Here's the results of just Tom Calderwood. And one thing I failed to mention, and the reason I wanted to pursue this, other than I just always wanted to try this, is that Tom Calderwood's in Oregon in winter. And so he does not have a good climate for doing photometry. He's battling clouds a lot worse than we are in Arizona, where I was able to get maybe every other night or so. He's not able to do that well because he's just battling clouds all the time. So there's his measurements, and then here's my measurements added on to it. And this goes all the way up until the middle of April, when Betelgeuse was now getting too low into the evening twilight, and then I had to stop, and Aldebaran as well. So there's one thing about this that seemed wrong, seemed like instrumental errors on my part, but I'm not so certain that's the case. So if I add Calderwood is in red, he's got the real good photo multiplier set up, and he's used to doing these bright objects. Here's my stuff in blue, and I never really, with a lot of head scratching and asking around, got why this was so different. And I showed these small scale fluctuations from day to day. So is that really happening or not? And the way, okay, and I keep mentioning this check star, which should have a magnitude that's known of 4.08. And that's the way that you decide how good is the photometry, where I'm doing this stuff right here, where I'm getting Betelgeuse jumping all over. And it's actually pretty good. Here's a line going across this plot of our check star at 4.08. And these are my measurements that I'm getting. So I'm typically within 20 thousandths of a magnitude. And these things are a lot bigger than 20 thousandths, these excursions from day to day. So whether or not that's really happening, I'm still not certain, but I kind of am confident that this part of it is okay. What's happening out here where these errors start getting real big is now the star is sinking, where I can only see it, I can only observe it. It only gets dark when it's 40 degrees or 30 degrees high in altitude. and that's a problem. So at that point, the results start getting a little bit more shaky. So to kind of put all this together, I know I rushed through this really fast, but to put everything together, I showed this slide earlier that had the past decade of measurements of Betelgeuse before this event that happened. And here it is with mine and Tom Calderwood's photometry, actually with just mine over here, that's showing what happened in this past year. So Betelgeuse got all the way down to almost exactly as bright as Bellatrix, which is the one that's at the same declination about as Betelgeuse, and got all the way down to 1.65, 1.7 before brightening. And then the nice part is it got almost up to its normal 0.4 magnitude before it got behind the sun. So we didn't really miss much on the brightening. So the things that were noteworthy are just how deep it is, and also these rates, the slope of these curves, both the descent and the ascent in a light curve are really steep. And so there are actual direct images taken at Paranal by the SPHERE instrument on 4 8-meter telescopes working together that show that this is like a dust torus that was around Betelgeuse. So it's not really that exotic of an explanation. It certainly was never going to go supernova, but a lot of people got pretty excited about that. And I just kind of ignored it and plowed on. And I thought this was cool enough to see something like this. And then to learn how to do photometry on something that's not what I'm set up to do. So the second to last slide here is just showing, and I should say what that is, that's the American Association of Variable Star Observers. That's what all these plots have been and all these references. So they give a data usage report that they send to me where people are using my data. And so it got a lot of views. This is just 1 week of data, and a lot of it's by students. You'll see STU in here, and amateurs and educators, that kind of thing, and professionals. So the data does get used, and you know, there'll be new models of Betelgeuse that'll come out of this. And so that's my presentation. I know we're not going to have time for questions, so hopefully carry on with the rest of the meeting. If people want to write me on Facebook Messenger or email me, that kind of thing, that would probably be the best way to do questions for this.
Tom, there was two short ones.
Yep.
Are you taking that, Gordon?
No, you can.
Okay. Yeah, one was, what application do you use for those plots and other image analysis?
Okay. So for this plot, this is a plotter that's at the AVSO site. For these plots, I mean, that's Excel that I bring the stuff into, but I do the actual data reduction was done using Maxim DL, which a lot of people use to run their cameras and to do the calibration of the images. And it does photometry that was good enough for what I was doing here. It gives me instrumental magnitudes that I was able to use for that.
And the other question was, if you, off the top of your head, remember what the full well of the CCD camera is?
It's a 16-bit camera, so it goes, I guess we're just asking for the bit depth, so it goes to 64,000, but we'll start, even though it's not an anti-blooming camera, which makes it better for photometry, it'll start to go nonlinear at about 45,000 ADU. So I make sure that I was well, all of this stuff, I was down at 30,000 or 35,000. That's kind of where I make sure I'm not getting into that nonlinear range of the sensor.
Right, and you cut down the light so you don't saturate that each of the pixels.
Yep.
Okay.
All right, so that's my technical presentation.
Thank you.
All right, thank you, Tom. Comments that I've been getting, a lot of comments here is in the chat portion is, great job, Tom. As always, you always do great presentations. We appreciate that. One of the things I failed to mention, it was my fault, gang, is down at the bottom in the chat room, there's or in the bar down there with the buttons, there's chat, which you can type in general questions, other people, make comments, just general types of things. Over to the right is Q&A, where you actually, if you have a question to ask the presenter, is type it in there. Now, there might be a lot of questions going on, so Tom Mosden and I, we go through that and weed through, because sometimes there's doubles, things like that. And then we will ask those of the presenter when the presentation is over. So you can ask questions of the presenter in there. Then that way too, we're not slowing down the presenter on his presentation. A couple questions came up about when we think we were going to open up, Greco open up EVAC for meetings. We don't know. We don't know, especially with the easing of restrictions that are happening now. We don't know what the future is going to bring. Are things going to get worse? Things going to get wetter? Well, weather better, I should say. So what we can do is sort of lag the public. As a club, we're not concerned about financial issues. That's plaguing the economy, the governments, is because the health and the economic concerns, they're inversely proportional. One goes up, the other one goes down. We don't have a financial problem. So the board of directors, we are all concentrating on safety. Safety of the members of the club and safety of Greco volunteers, of outreach volunteers. So we are concentrated on safety. Right now, we don't believe that it's safe to do any personal contacts. That will change in the future, but right now we just don't know when that's going to be. Again, look at our website. That's where we'll post our latest information. And Tom Mosden, if you want to introduce our main speaker. By the way, Tom Mosden, our vice president, is the one who coordinated all of this. He's the one that came up with the idea. He got the practice one last week going. So Tom, thanks a lot. Thanks a lot for everything that you do for the club. So Tom Mosden, I'll hand it over to you.
Okay, thanks, Gordon. I'll introduce Adam here. There we go. Okay, Dr. Adam Beasley is currently a National Science Foundation Astronomy and Astrophysics postdoc fellow at ASU. He's also principal scientist for the Murchison Wide Field Array located in Western Australia. And he's also a collaborator on the a $7 million NSF grant titled HERA, Unveiling the Cosmic Dawn. HERA is another low-frequency array. And he's also principal investigator of another NSF grant titled Characterizing the Stars and Galaxies That Drove Reionization. And Adam's talk today is titled Radio Arrays to Map the Cosmic Dawn. And normally we'd have applause as Adam takes over the podium and gets mic'd up, but here I'll just stop sharing my screen and hand it over to Adam. Take it away, Adam.
Thanks, Tom. While I get set up here, I'll just say thank you to the organizers for having me come and give a talk, and thanks to everybody in the virtual audience. This is kind of fun. This is my first talk through my first virtual talk during this pandemic, so it should be interesting to see how this goes. So I guess a little bit more about myself. As Tom mentioned, I'm a NSF postdoc at ASU. I come from kind of a physics background, so it's fun to see all this, all the astronomy that's being done on your guys' end. Tom just gave a really awesome presentation. A lot of it is, I'm not familiar with all of the optical astronomy stuff, so I take kind of a physics approach. And but this talk is going to be a pretty just general overview of radio telescopes, specifically ones at low frequencies, and I'll talk about what that means in my mind anyway, a little bit later on. And the last thing I just wanted to mention is that I'm at ASU right now, but in the fall I'll be starting a faculty job at Winona State University, which is in Minnesota. Okay, so I guess I wasn't exactly sure what the audience would be. So again, I just kind of took a pretty broad look at things. So we'll start with kind of some of my like standard deck of science motivation slides. So I'm sure, you know, a club like this, you guys are very familiar with some of the astronomical objects that you can observe with telescopes or even with your naked eye, some of these things. And so this is our very like Earth-centric view of our solar system. And then if we kind of look out into the sky, you can kind of see larger objects, so more stars and clusters of stars and things like that. If we look further out, you start to see the galaxies. And the kind of point that I'm trying to make here is not just like that there are these objects out there, which you guys all know, but that the further out you look, you're actually seeing the universe as it was at a different time, because the light takes the time to get here. And so the further back you look, you know, if you look at kind of the nearby stars and galaxies, you're seeing things in kind of on a cosmological scale roughly at the same time. But if you look at further away galaxies, you start to see actually the universe itself evolving and unfolding. And so this is kind of just showing that you zoom further and further out, you start to see kind of proto-galaxies. If you go beyond that, you could even see what there was before galaxies, which would be mostly just gas in the universe. And so I should point out that, you know, very powerful telescopes like the Hubble Space Telescope and I always say the soon to be launched JWST, I've been saying that for at least 5 years, because it's always 18 months away from launch. They can see galaxies out pretty darn far, but you know, there's always going to be kind of a limit to that. And so there's this kind of giant gap in the history of the universe where we can see out so far to see galaxies, and then we can't quite reach further than that. But there's a very bright thing even beyond that. You may have heard of the cosmic microwave background. And this is the moment in the history of the universe. Again, the further out you're looking back into time. And the cosmic microwave background is coming from the time when the universe had cooled enough that protons and electrons recombined into hydrogen gas, and they let out kind of a glow at that point. And in fact, most of the photons in the universe are from that kind of afterglow of the Big Bang in that background. And then, you know, if we can peer beyond that, you know, we can see there's more physics to be probed, things like inflation and baryogenesis, nucleogenesis. Those things are, we're not going to be able to see it with light, but you may have heard of the, you know, gravitational waves, which were first detected a few years ago now, opened up a brand new window into the universe. And in theory, we can detect gravitational waves from that time before the cosmic microwave background. So, it's, you know, in theory, we can see, you know, the entire universe unfold from its birth. But what right now, the kind of state of the art is that we do have very strong detections of this last, what we call the surface of last scattering around the cosmic microwave background. And of course, we have more local observations that are kind of coming out from the other direction with a gap in between. And that gap is kind of where galaxies first formed. So this is a very kind of cartoon picture that I found on Wikipedia. And I'll show another cartoon picture. This one is meant to have, and the joke is that every cosmology talk will show you the history of the universe stretched so that the time period that the cosmologist is interested in is the most prevalent period in the cartoon. And so I'm showing on the left is the Big Bang, so the beginning of the universe. You can see that kind of green tint is meant to be the cosmic microwave background. And as you progress towards the right, you see like immediately after the Big Bang, well, okay, so the Big Bang itself is what we call recombination, with the electrons and protons recombined. And at that point, the universe is filled with neutral hydrogen gas. There's a very trace amount of helium and lithium, but it's almost entirely hydrogen gas, and it's neutral, and it's basically just a diffuse gas. But as time goes on, the universe continues to expand and cool. That gas will condense gravitationally and start to form galaxies. I missed the dark ages. So during that time when we just have the neutral hydrogen, there are no sources, there are no stars or bright explosive vents or anything like that. So we call that the dark ages because there are no stars to light up the universe. But when the galaxies start to form, and they're kind of depicted with these yellow dots in here, they will emit light, specifically ultraviolet or ionizing radiation, which will then go out to the gas in between all the galaxies and reionize it. So on the very far left, during the Big Bang, you had a hot plasma. It cooled to the point where you had neutral hydrogen gas, and now you have these first stars and galaxies emitting ionizing radiation, which will reionize the universe. And so a lot of my time is spent trying to probe reionization and the dark ages. That's kind of the cosmic dawn, if you will, as stars turn on and the universe becomes light, and we can see all the wonderful things that you can see with your telescopes, your optical telescopes, like modern galaxies and stars and things like that. So there are instruments built to probe these things. As I said, we do have measurements of the cosmic microwave background way off on the left. That comes from telescopes like Planck or WMAP or a number of other ones. And then on the right, you have telescopes like JWST or Hubble Space Telescope or your ground-based telescopes. And the radio arrays are going to be used to try to fill in that gap in between. So I highlighted here Hera, which I'll talk about later in the talk, which is designed to try to detect the hydrogen gas during the first stars in reionization. Okay, so I've said hydrogen gas a number of times. I always like to, oh, I'm sorry, I totally forgot about this slide. So this is that epic of reionization again, just to show kind of an animation of what this looks like. So the dots here are galaxies in a simulation of a volume of the universe. And as time progresses, they're going to create these kind of bubbles around them of the ionized medium. So they're ripping apart the protons and electrons around them to form these kind of bubbles that grow, and it becomes this kind of Swiss cheese. And eventually what you get is those bubbles will start to overlap. And what we have today is a bunch of galaxies, and all of the gas between the galaxies is ionized. Okay, so the slide I thought I was getting to, hydrogen gas. Can anyone confirm that you can hear me? My headphones just died.
I can hear you.
Okay, sorry about that.
Yeah, no problem here.
Cool. Sometimes my headphones just cut out. So I've mentioned hydrogen gas a couple of times, and I always like to motivate why we care about it with this slide. So hydrogen is composed of a proton and electron, and they can exist in various states. You probably remember from your high school or college physics or chemistry classes. But there's one specific transition between two states from when the proton and electron are anti-aligned, so they're facing in opposite directions, and they will spontaneously just flip and align themselves. And when that happens, you have a drop in energy, and that energy is released in the form of a photon at a very specific wavelength at 21 centimeters. And this signal has been used for humans to understand the universe around us, and we find it to be so kind of fundamental to our understanding of the universe that it's how we chose to
kind of define units when we sent this Voyager record out into space. So you're probably familiar with the Voyager record. It was kind of a Hail Mary, you know, signal to ET as we sent these Voyager spacecrafts out to the interstellar medium. And the idea is if some species out there picks it up, we wanted to be able to send a message. And it's an interesting problem to think about, how you send a message to a species that you have no kind of common reference with. And so some very smart scientists and artists and creative types came together to come up with this, like, how to do it, what to send. And the thing that I find really fun is to think about how they establish a language. And they do it by, you know, so on the left side, you see it's basically a record. On the right side is the back side of the record is instructions, how to use the record. And, you know, you can work through all of decoding it. If you've never done it before, I suggest trying to pick it up without the solution and see if you can work out what they're trying to say here. It's kind of a fun game. And then once you actually get to the record, you see what's on it, and you get to kind of try to puzzle out everything else. But if you see in the bottom right corner of the record is this kind of pictogram that I have for the hydrogen atom transitioning. And this is how we defined time and length on this record. So you want to say, you know, this is so many seconds, or this length is so, you know, this big. How do you do it? Well, they use these kind of fundamental ideas that we have about how, like, this signal that we can see out in the cosmos to define time and length, to kind of establish things like, here's how fast you need to spin the record. Here's, you know, what, here's how big a human is. Here's how far away we are from different pulsars, so you can find us. Anyway, this is kind of a complete aside, but it's just a kind of interesting example of how, or an illustration of how important 21 centimeter is to our, to astronomy, I guess. So 21 centimeters is the wavelength of the light when it's emitted. But when you're observing things that are very far away, and the universe has time to expand while the photon is traveling from the source to us, it actually, the wave actually expands and stretches out, and you measure it at a different wavelength. So in this little example, it has stretched out to 1.5 meters. We refer to a redshift of 6.1. You may have heard this term before. It's used in a couple of different contexts. Sometimes it's referring to the stretching of the wave when something is just moving away from us. This redshift is what we call cosmological redshift, and it's due to the universe itself expanding. But you can actually get information out of it. So if you have two hydrogen atoms hanging out in the cosmos somewhere, one emits a photon and it starts traveling towards us, and then a little bit later it passes another hydrogen atom and it emits a photon. It turns out, you know, that one has already stretched a little bit when it meets up with the other one, and by the time they both get to us, they're at slightly different wavelengths. And you can use this to form what we call a spectrum and look at different wavelengths and see, you know, how much hydrogen gas, or how hot that hydrogen gas was at different locations in the universe. And so there's this kind of relationship between wavelength. You also might know that there's a relationship between wavelength and frequency, but also the distance and the time in the universe. So I kind of like throw all these axes up here to kind of show you that cosmologists like to interchange these things a lot. So my apologies if I keep going back and forth. I don't think I have too many references to specific wavelengths or frequencies or things like that in this talk, but it's just kind of a note that these things are all kind of intertwined together. And there's a nice analogy to this, which is to look at the ice cores that you can pull out of ice sheets in glaciers or in Antarctica, where you get a nice history of the area by just pulling out the ice and looking at it at different times in the history. So that's kind of like an analogy of what we're doing here. Okay, so where can you find hydrogen gas? Well, it's basically everywhere. So, during the dark ages, it's pretty much all that there is. So you can have telescopes that are built to detect very low frequency, long wavelength light that was emitted at 21 centimeters and has stretched out. So we have a couple of instruments that do that. Edges, I'm guessing you guys may have heard about. Tom Marsden has worked on that project. Hera, again, I work on it. I will talk about it in a little bit. And the MWA. So, and as I'm kind of moving across here, we are looking at slightly different times in the history of the universe. So these last three are all looking for the epoch of reionization. There are instruments like CHIME in Canada that is going after hydrogen gas in galaxies that are post-reionization, but kind of pretty far away from us, and looking at structure formation and evolution. You can probe things like dark energy by looking at how galaxies, how this large scale structure changes over time to see how the universe is expanding. And then you have things like the VLA and Arecibo that look at hydrogen gas more close to us at roughly that 21 centimeter wavelength. I'll go into a few of these telescopes in the talk here. Okay, so one natural question is like, so okay, we build our radio telescope, we look up at the sky, what does it look like? So this is a kind of composite made using the MWA, the Murchison Wide Field Array, and it comes out of the GLEAM survey. And there's a lot going on here, as you can see. So there's the galactic plane in the center. The galaxy itself is very, very bright at these frequencies. So this is between, I think, about 100 to 300 megahertz, give or take. There's things like, I don't have a mouse. Kind of above the galactic plane, you can see a big swooshing shape. That's North Galactic Spur, I believe, which is a supernova remnant that we're kind of basically inside of. There are other various supernova remnants along the galactic plane that you can probably pick out. And then there's all these dots all around. And those dots they look like stars, but if you're familiar with radio astronomy, you probably know these aren't stars. Every one of those dots is an exploding galaxy. So they're very far away. They're very energetic, emitting the radio frequencies. So you just look up and you see just all kinds of stuff in radio frequencies. But that signal that we're looking for, that from the epoch of reionization, is far past that. So everything that I showed you in that previous slide is what we call a foreground. It's in front of us. It's all these galaxies that we're trying to look past to see this the signal from reionization. So it's a big challenge, and I'm just going to kind of talk a little bit about some of the instruments that we use to go after the 21 centimeter signal, kind of introduce you to a few different techniques that are out there, and hopefully you'll come away thinking that it's some pretty cool stuff that we're doing. So types of radio telescopes, you can sort of categorize them into two categories, though it's not as super straightforward as you might think. So on the left side, you have single dishes, and that's FAST, which is in China. It's the largest single dish in the world. It's, I think, 500 meters in diameter. It dwarfs even Arecibo, which is 305, I think. And then on the right, you have interferometer arrays. So these are many dishes or antennas that work together to form one telescope. So when you are taking a single dish approach, big dish is small stuff. So you can, the bigger the dish, you can resolve smaller things. Generally at these frequencies, you're going to be diffraction limited. And so this kind of equation that I have up there is, and I think it's like, okay, it's the second equation in the talk, but I think it's the last one. just shows the solid angle that you can resolve with this telescope, and it's the wavelength squared divided by the area of your aperture. So you want to see small things, you build a big dish like Arecibo here, which is basically built into the mountains in Puerto Rico. And then you generally have like a detector up at the focal point. Arecibo actually has a second mirror, and so there's another mirror inside of that kind of dome. And this guy functions by to point the telescope. You move the entire focal apparatus around. So that the cradle, they call it, it gets moved around and shifted to look at different parts of the sky. So it's sort of like if you had a CCD camera and you kind of move your one pixel that you have, you move it around to different parts of the sensor. But dishes aren't always dishes. So there are a few examples where rather than having these big reflectors, you just kind of sample the light as it comes in directly. So on the left, you have the very first detection of astronomical 21 centimeter light came from these guys, Ewan and Purcell, where they built this horn, which feeds into a little waveguide, and then down in kind of the lower left would be a simple antenna. I think it's basically just a wire that detects the photon as it comes in. And then on the right, you have more modern examples. So EDGES, as I mentioned earlier, and PRISM, which is a similar experiment. So these guys are very small. They're about the size of a tabletop. And the idea here is that if you don't care about the small stuff, maybe you want to look at very big stuff. And so you need that solid angle equation. You want to have a small telescope so you can see larger things. So, like I said, these kind of categories are kind of flexible. And the other thing is you can have a focal plane, a focal plane array. So even if you have a single dish like Parkes here, you can put a series of detectors up at the focal plane. And this, again, is like a CCD camera. You can detect several different points of the focal plane at the same time and get a wider field of view that way. So you can see larger things and still have still have the resolution, which is nice. I should also mention Arecibo also has a focal plane array as one of its instruments, but I could find a nicer picture of Parkes, so I went with that. Okay, so I'm going to shift gears a little bit to radio arrays. I am guessing that being in Arizona, most of you have probably seen this, at least in the movies. A lot of you have probably actually been out there to see the very large array, which is an interferometer. So how does that work? I like to use this analogy. So you might remember the two-slit experiment from physics classes. If you were to shine a laser through two slits and then look at the light on a screen, what you see is that light goes through the slits and then interferes, and you see this kind of interference pattern on the other side. It's kind of like almost like a sine wave. It kind of oscillates between a maximum and a null. Well, the physics is exactly the same, and I'm not going to go into the details, but the idea is that the physics can be run in reverse, and what you have, if you were to put down two antennas and measure the signal from whatever you have out in the sky, you can correlate them, and those correlators are basically large computers. You can build up a response to a wave like this. And let me see, I think my next slide, yeah, I'll just go to the next slide. So the concept is that two antennas working together have this kind of response to a certain structure on the sky. And what you can do is you take more of those antennas. So, and this is a very crude simulation. It's not actually, a detailed analysis of how this works. But this is the idea is like if you take a few antennas and you combine those responses, you can start to kind of see a blurry picture. But as you add more antennas or more slits, you can start to resolve the structure in the sky. And the idea is you are accomplishing that large aperture, that large dish, by using a bunch of small dishes or small antennas together and combining them electronically. So we like to say that our computers or our telescopes are 80% computer. What we're doing is we're sampling the signals rather than focusing them with a dish or a lens or something like that. We're sampling them directly and then using computers to do the focusing. Okay, so enough about that. I'm just going to kind of go through and show you a couple of telescopes that I work on personally. The MWA, which is the Murchison Wide Field Array, and Hera. Both of these are built to detect the reionization signal, 21 centimeter reionization. So they're built to kind of detect the same thing, but they took very different approaches. So the MWA is a very general purpose observatory. It has, you can do all kinds of different science with it. There are 4 kind of main themes to the science. So the cosmology I've been talking about, but there are groups of people who use it to study time variable events or phenomena. People who use it to study the sun, the heliosphere, and the ionosphere. And then there's the last category, which is kind of a catch-all galactic and extragalactic science, which is basically everything else. So you can study almost anything. And the MWA itself is actually, it's an open instrument. Anyone in the world can apply for time on it. It is something we like advertise. If you're interested in it, that's great. I do warn you that it produces a whole lot of data, and the data does not look like images. It takes a lot of processing to get to the point where you have images. But in principle, it is something that anyone in the world can apply for time. And like I said, a lot of data. We've been collecting data since 2013. We have over 35 petabytes, and a lot of that data is public. If it's older than 18 months, you can just go on the internet and download it. Yeah, so this picture that I'm showing here is a single antenna. You can think about it as kind of like a dish, but again, dishes aren't always dishes. This is an aperture array, so you have 16 dual polarization dipoles that their signals are all combined together to form the signal of what would be just one dish in an array. And there are 256 of those out in the desert. So why are they out in the desert? I don't think I have to harp on this too much with this group, but I'm sure you're familiar with light pollution. We have the same problems in the radio regime. This is radio.garden. You can go to this website and listen to radio stations across the world. It's kind of fun to just browse while you're studying or doing whatever. But you can see there are a lot of radio stations in the US and in Europe. But if you go out to the Western Australian outback, suddenly there's a lot fewer radio stations to compete with. So that's what we did. Out to the Australian outback. This is the fun one because I get to sit back and show you a movie. So this is just a drone flyover of what we call the core of the array, where we have a lot of antennas kind of crammed together. And that gives you a lot of sensitivity to large stuff. Like I was saying, these things are sampling these response patterns. And so we're kind of zooming out to see all of these antennas out there. This is during phase 1, where we had called a pseudo-random core. Those are things that are kind of placed sort of randomly. And as you zoom out, there are a lot more antennas that extend out to a radius of about 1.5 kilometers. It's really hard to pick them out in the desert, and it's even harder when you're standing in the desert and you get lost. You don't know which direction is home. So be careful if you go out there. but they are out there, I swear. I don't know if you can see my mouse, but like there's one over here. There's one just off this little spoke of a road. So yeah, that was that one. And then in 2016, we upgraded it to phase 2, we call it, which it has 2 observing modes. One has these hex cores, so more antennas kind of piled together, this time in a pretty regular grid. And I'll say a few words later about why that is. And these kind of hexagonal patterns, but we also extended the longer or the further out antennas to reach a total diameter of 5.6 kilometers. So we can get the resolution that you get from having a dish that is 5.6 kilometers, but we don't have the giant infrastructure of having such a thing. You can do it with these smaller antennas. And I don't know if I said it earlier, but the key here is that, you know, why didn't we do this from the start? And the reason is that in order to do the data analysis and to turn these apertures into a full telescope, it takes a lot of computing power. And with computing power ramping up, as always, you know, Moore's law says we're doubling every so often. We've gotten to the point where we can actually build these things and process the data. So that's kind of the reason that these telescopes are becoming more and more popular, and you're going to see a lot more of them. This is just a comparison of an image that you get of Fornax A. On the left, you have Fornax A with phase 1, and on the right is with phase 2. And you can clearly see a lot more structure. You can better resolve the nucleus of the galaxy and lobe structure and things like that. Okay, so Hera, on the other hand, is a purpose-driven experiment. So Hera is a hydrogen epoch of reionization array. It is built to detect the EOR. It is not a general purpose observatory, so there are a lot of sacrifices that are made, essentially. So the MWA, you can point it in different directions. Hera is pointed straight up always. The MWA had a nice, I called it a pseudo-random layout, and that was for the purposes of having a nice point spread function, so you have good imaging fidelity. Hera has this very, very regular layout in this hexagonal pattern. And the reason for that is that by laying them out in this redundant way, you are measuring the same response pattern over and over again. And that gives you more sensitivity. So trying to detect something that's very, very faint, it helps if you do it many times and you're able to combine the data. There are other reasons for it, which get into kind of far too technical for this setting, but the idea is that you have to calibrate these things, and if you're measuring the same thing over and over, you can use that information to fish out the calibration so you understand how each antenna responds to a different signal in the sky. Rather than being in Australia, Hera is in the Karoo Desert in South Africa. Again, looking for a place where there are very few radio towers and things like that. So you want to find a place where there aren't people, essentially. Hera is under construction. So each of these dishes is 14 meters in diameter. Let's see, what was I going to say about this? I think that might be about it. You can see a person down in the lower right to kind of give you an idea of how big that is. In the end, the kind of core region of Hera will be roughly the same size as Arecibo. Here's an aerial photo of it under construction on the lower right, and then up above you can see Meerkat, which is a pretty famous telescope, and it made news. This is probably like 2 years ago. It had its first light and made some really amazing images. Meerkat is the square kilometer array mid telescope, or the start of it, I should say, if you're familiar with that. Hera is undergoing an upgrade to change out its feeds. So this would be like the detector in the telescope. There are these giant Vivaldi feeds, which are look like medieval torture devices, but I swear that they're really just there to detect light. That's a picture of one of our grad students helping to install one of them. And this is just a quick movie to show the progression of our commissioning as we build out antennas. So you can kind of see we built them out with some feeds and then took them all out and then replaced them with Vivaldi feeds. So right now we're at, I think, about 300 dishes. With COVID, things are stalled for now, but we hope to ramp back up once things start opening up again and complete the array. In the meantime, we are taking data with the array as it's being commissioned. And this is just a little movie of one night's worth of data using 67 dishes. You can see there's going to be kind of a region in the center where we are sensitive to. We call that our primary beam, but then you can see sources kind of come in and out as they drift overhead. So again, Hera does not point, it just looks straight up and lets the Earth move it. So you can kind of see different sources going through. That's Fornax A, that really bright thing, and various other sources. I should really label these at some point because I don't always know the sources. You can see kind of both small point sources, but you can also see kind of diffuse things, which is probably things in the galaxy like galactic gas and things like that. Yeah. And that movie was created by our undergraduates at ASU, which is kind of cool. Let's see, how am I doing? Oh, I think I'm okay on time. Cool. So I was gonna just give you kind of a look toward the future in a project that I work on with the idea of trying to move towards these very large arrays. So Hera itself is a pretty large array. It has 350 antennas. It's processing 200 megahertz of bandwidth at a time. That's a lot of data to crunch through. And inside of the telescope, the data rate is approximately the total internet traffic, like the global internet traffic. So you go to arrays that have 10,000 antennas, and that computing is going to be, even Moore's law can't save us. It's not going to go fast. Like we need to find other methods. And so there's a concept of direct imaging, which basically takes the signals, and rather doing this correlation that I've kind of alluded to, it forms the images of the sky on the fly, which can be very difficult to do. There are certain reasons that it's hard to do, but if you can pull it off, it will actually lower the computational cost because we're taking advantage of something called the fast Fourier transform, which scales much nicer than trying to cross-correlate antennas. And it will produce images in real time at high time resolution, which is kind of a nice little side effect. So I work on a project that was setting out to lower the computational cost for future arrays, but we realized that the more immediate application is to get access to this very high time resolution data. And another thing is that the output bandwidth, the speed at which you have to write down the data is also very low. This is just a quick comparison showing for a few different telescopes, like how fast you have to be able to write down data in these two different methods. So a couple of years ago, we set out to kind of do a proof of concept for this. We took an existing radio array. This is the long wavelength array station in Sevilleta in New Mexico. So it's related to the telescopes that are down in Socorro, where you probably have come across the VLA. Next to the VLA is the LWA-1, the first long wavelength array station, and then this one is it's about 30 miles north of that, is another station in the Sevilleta Wildlife Refuge area. So what we did was we took the array as it was and just reprogrammed the GPUs. So just reprogrammed the computer. And this kind of is emphasizing again how much these telescopes really are like computer telescopes. We were able to not touch the hardware at all and just reprogram it. And so we did that, and we have kind of a proof of concept. So you can make these images, and these you guys are probably used to seeing very high resolution, relative to what I do, very high resolution images where you can see individual stars. Well, that's not anywhere close to what we do here. The circle here is the entire sky. So you have the North Pole at this intersection here, the North Horizon up above, the Southern Horizon down here. You can see the galactic plane coming over here on the west, and the Cygnus A there, and I think is Cassiopeia A up there. So this is just a single frame, but we created frames every 50 milliseconds I think we did it like for a night. And if you play that movie, you can see there's like little blips. This is RFI, radio frequency interference, but this is the interesting thing. This is a meteor that was entering the atmosphere, and as it entered the atmosphere, it creates like a plasma trail around it, and that plasma trail will reflect TV signals coming from a TV station. This one happens to be one in Mexico. We can look at the frequency to determine what station it is. Essentially, this is at, I think, 55 megahertz. So the signal from the TV is reflecting off of the meteor, and then we're seeing it in our telescope. So that was, I thought, pretty cool. So, you know, we continue to work on this to kind of further develop these technologies that will enable the future arrays of tens or hundreds of thousands of antennas. And in the meantime, look for some cool things like meteors, and we're trying to see if we can detect FRBs, fast radio bursts, which are a pretty hip news item these days, especially at low frequencies. Okay, so I think the very last telescope that I was going to mention is very different. This is the completely hackable amateur radio telescope. So you may recognize the structure of the telescope. It looks a lot like that early 21 centimeter horn. So that horn was in the 50s. This is today. And the goal of this project, so I kind of advise it and help students, but they are doing all the work. They are designing and building this telescope to detect the 21 centimeter signal. And the idea is that the telescope is supposed to be accessible to a very wide audience. So I have a couple of undergraduate students, but we're reaching out this summer to high school students. And the idea is that, you know, hobbyists can pick up the project and do it themselves. There's a website where you can go if you're interested. It's a work in progress. So Bree on the right there has been developing our website where we have tutorials on how to set things up. We were able to actually detect the signal. We took it out to the Lost Dutchman State Park last summer, and we're able to detect the signal, which is pretty exciting. The goal is to have the cost of the telescope down to $100. That includes the computer. So we use a Raspberry Pi. It's currently there. Most of the components cost about $130. And then there's this filter that costs about $500. So the filter is the thing that we're working on. We're basically going to try to redesign it to have have something that a hobbyist can pick up and build themselves to replace that very expensive one, because it doesn't need to be that expensive. That's just kind of the one that we found and used to prove that we could do it. So anyway, that was just a little plug for chart here. I think I'll just conclude with this slide, which kind of just gives a few websites where if you have questions or want to read more or see more on some of the things that I've talked about, you have the website for the MWA. Reionization.org is the website for HERA. This is my personal website, which is a little bit out of date, but it has useful information on it, and then the website for chart there. And I'm happy to take any questions.
Thank you, Adam. Give you a lot of virtual applause. Yeah, there are a couple questions queued up. One of the early ones was, I think, back to detecting the cosmic dawn or epoch of reionization. It's like, how do you differentiate between stretched hydrogen signals and other stretched signals? Is there any overlap in final receive frequencies between different elements?
Yeah, that's a really good question, and it's kind of the thing that plagues us. So there isn't. This is a very low frequency atomic or molecular or any like type of transition like that. So there aren't overlaps as far as that goes. Where you do have a lot of overlap is other processes like electrons spinning around in magnetic fields and emitting synchrotron radiation. So all of those images that I showed you, kind of the foregrounds, those are emitting light at the same frequencies that we're trying to detect the stretched out 21 centimeter signal. And so it's a very difficult thing to decouple those things, though we do have kind of mathematical tools for doing it. And in fact, I have a backup slide on this that I won't spend too much time on it, but the concept is that if you look at the spectrum, so looking at the intensity of the light versus frequency, the foregrounds, which are very, very bright, these bright galaxies, are very smooth. But that 21 centimeter signal, it has that kind of Swiss cheese look. It has that, here's a galaxy, here's a hole, here's other things. So it has this bumpiness to it. And so if you can filter out the foregrounds, you should be able to see that 21 centimeter signal below it. And I usually make an analogy with sound and fun stuff. But the idea is you can kind of convert it into a different space where you put all of that power from the foregrounds on one part of the spectrum, and you end up with everything else. Hopefully an area where the 21 centimeter signal is brighter.
Okay, and let's see, one other one. Do you take the Nyquist frequency into account?
So I'm trying to remember the exact back end for Hera. I think that we're using the first Nyquist zone. Yes. So one thing is that these telescopes are sampling the electric field directly. So we're actually sampling like those sine waves and things, and you're able to do a transform to the frequency of observation pretty much directly. Of course, you can have aliasing, so there are a lot of filters or bandpass filters that will kind of ensure that the signals that you're looking for are not being aliased from outside your band into your band. So I hope that answers the question. The general answer is yes. I know that people coming from different directions think about these things very differently, so my answer might not be super satisfying. I understand that, but yes, we are making sure that we are detecting and sampling the waves appropriately.
Okay, and then there's another question. It's a little bit vague. Just, have you ever used or built an itty-bitty radio telescope? I'm guessing they're asking for one smaller than the MWA ones, or
so is the itty-bitty like an extension of the very small radio telescope? I have toyed around. So CHART, the project that I talked about, is based on the very small radio telescope. It seems like they always kind of just keep going. There was a small telescope and there was a very small radio telescope. The problem I had with those, and I'm not familiar if itty bitty is a branded thing or not. But the problem I had with for example, the very small radio telescope was that it required very specific and obsolete parts. So when they were building it and designing it to begin with, it required, or they found they were able to save costs by repurposing things. Some of those things that they were repurposing were things that were very specific and you just can't find anymore. So when I'm kind of, so the one of the guiding principles behind CHART is to try to make it robust against obsolescence, so that you can swap out parts if you need to. We're trying to build these tutorials and things so that the user can read and understand why we choose what we do, and if they need to in the future change things out, they understand what they're looking for. It's also, all open source. We use open source tools like a new radio. Our code is open source. We try to use open hardware as well, like the Raspberry Pi. I'm actually not sure if our software-defined radio is open or not, but yeah. So again, I'm not sure if that answers the question, because I'm not familiar with EBD radio. Maybe that's the answer to the question.
Yeah, he agrees that I think you're talking about what he was thinking of.
Okay.
And what are they used for the rest of us that may not have heard of it? Do you know what they're used for, Adam?
Oh, I'm sorry. What are used for?
The itty bitty telescopes?
No, because I don't know if that is a specific brand
or the chart, the ones you were talking about.
Chart. So chart is our kind of base design is to detect the 21 centimeter signal within our own galaxy.
It is, okay.
It's meant to be flexible, so you can, if you want to take the software and the radio and go for diurnal variation of our galaxy in a different wavelength, you can go do that. That's the hackable part of it. It's meant to have different purposes for whoever wants to do different things. Maybe someone wants to go design their own back end or their own front end electronics or something like that, if you're really into that kind of thing.
Okay, I think that's the last. Oh, one more. Yeah, I similar to what I was saying. What science could a small radio telescope builder do that would be of value?
Yeah, so we'd like to explore that more as far as the actual science. Like, you can do things like measure the rotation curve of our galaxy, which is kind of cool. It's been done. It's been done on the cheap like this before. One of the directions I'd like to take that is towards a kind of citizen science type project. If we can incorporate GPS timing, we could in principle build like a long baseline array similar to what you may have seen with the Event Horizon telescope that was able to measure a black hole. Now, we wouldn't be able to measure a black hole, but you could try to synchronize things so you can look for transient events. There might be interesting things out there like that. Or measuring ionospheric properties, the sun. There's a lot of fun things that happen in the radio. I think it needs some exploration, though, to see what things are actually feasible with those small telescopes.
All right, thank you. I think that's the last question that popped up. I'll turn it over to you, Gordon.
Yeah, looks like that's it. Thanks, everybody, especially Tom Osden, for putting this all together. This is a new chapter in EVAC's club. So what we'll do is the leadership team, the club's leadership team, will get back together and we'll chat about this and see what improvements we can make and what the future is for this. This is brand new stuff to us. Exciting, right? One of the reasons we're in astronomy is all the new things that pop up every day and how we're always reaching for new and exciting new stuff, and it certainly is. So thanks, Tom. Now the internet, of course, is something that we are familiar with. Lots of good stuff on the internet. but also bad stuff, and plus some old stuff too that you don't know exactly how old it is. Hopefully this will continue on and we can do these virtual meetings and listen in. We had 61 attendees, and hopefully that this will grow just like our membership has grown. So that's it from here. I think, yeah, I think that's it. All our questions were answered. So if anyone else has any questions, get in there right now, or else we will close this down and say success for our first virtual meeting. So I'll give a countdown here. 3, 2,
Thanks,
1.
everybody.
That's it. Thanks, y'all.
Bye-bye.